Howdy. The purpose of this video is to provide some additional information and some examples of the inverse function theorem. You recall that in class we said that the derivative of f inverse of x is 1 over f prime evaluated at f inverse of x. And this result is the famous inverse function theorem, or IFT. Graphically, what we're saying is this. Suppose I have some function, f of x, whose graph looks like this. I can generate the graph of f inverse simply by reflecting about the line y equals x. And in so doing, I swap inputs and outputs so that the graph of my inverse will now look something like this. And every point a comma b on the graph of f will have a matching point b comma a on the graph of f inverse. What the inverse function theorem then tells us is that the tangent line at x equals a on the graph of f and the tangent line at x equals b on the graph of f inverse have reciprocal slopes. F prime of a is going to be 1 over f inverse prime of b, and vice versa. Notice that a here in the second expression is exactly the same as f inverse of b, and so we have the inverse function theorem just as advertised. So all of this makes some sense graphically, but when you work it out in practice, you have to do a couple of things to keep your head straight. So I'd like to do 3 examples here. And the first example is to use the inverse function theorem to solve a problem that we already know the solution to. I would like to find the derivative of the square root of x using the inverse function theorem. Now, we already know the answer to this problem. We know already that the answer should be 1 over 2 root x. But I'm doing this to show you how you might set up an inverse function problem. I take a look at the square root of x, and I'm going to identify it as the inverse of some function. And I don't think it's too hard to see that the function whose inverse it is going to be x squared, where x is greater than or equal to 0. So, with that in mind, we could compute the derivative of the square root of x as 1 over f prime of f inverse of x. And since f of x is equal to x squared, f prime is relatively easy to compute. That's equal to 2x. And f inverse is root x. So that putting the pieces together gives us exactly the answer that we knew ahead of time that we were going to get. So how did all this work? Well, it worked by identifying 2 components. First of all, we identified f prime. Second of all, we evaluated f prime at f inverse. And then that went directly into our inverse function theorem form. So, that's how it works out algebraically. Very often, however, these kinds of problems are done numerically. So I want to consider 2 examples, one without a calculator, and the second one is going to be with a calculator. Let's consider this question. What is the derivative of inverse sine of x evaluated at x equals 1/2? Well, we're going to follow the same pattern that we did in the previous problem. We're going to identify the inverse sign as an inverse function, which means that its parent function is f of x is equal to sine x. And now we're going to put the two pieces together. We need a derivative, f prime, which is cosine, and f prime of f inverse, which is going to be cosine of inverse sine. Those are the pieces that we need for our inverse function theorem. F inverse prime is 1 over f prime of f inverse. And therefore, f inverse prime of 1/2, when x equals 1/2, is 1 over the cosine of the inverse sine of 1/2. Now to evaluate this, by the way, this is a perfectly good number, so we could just stop here. Or if we had a calculator available to us, we could compute that directly on the calculator. However, if we're stranded on a desert island and we really need to find the value of 1 over cosine of inverse sine of 1/2, then we can appeal to the unit circle, working inside out. The inverse sine of 1/2 is the angle whose sine is 1/2, and that angle is pi over 6. So that we can replace the inverse sine of 1/2 with pi over 6. And now we evaluate the cosine of pi over 6 using the unit circle again, and get root 3 over 2, so that our final derivative has the value of 2 over root 3. The thing that we learned from this problem is the virtue of working inside out. We started with 1/2, found the inverse sine, and then built on that to find the cosine of the inverse sine of 1/2. Finally, I want to consider an example where we would use the calculator to compute the inverse. Let's take a look at the function that we looked at in class today. F of x is equal to x cubed plus x plus 1. Looking at the graph of f, it's clear that f does have an inverse because it is 1 to 1. It passes the horizontal line test. However, it's very difficult to write down an expression for f inverse. So if I wanted to evaluate, for example, f inverse prime of 4, then I would not be able to simply find an algebraic expression for f inverse and take its derivative. Instead, I would need to appeal to the inverse function theorem. And I would begin by writing down the form, just like so. And now the two pieces that I need are f prime, and I need the value of f inverse of 4. Well, f prime is easy enough. Since f is x cubed plus x plus 1, then f prime is 3x squared plus 1 plus 0. So that's that. But what about f inverse of 4? What I'm trying to do is I'm trying to find the x value that is equal to the f inverse of 4. In other words, I'm trying to solve the equation f of x equals 4. Notice that these two equations mean the same thing. Well, since f of x is equal to x cubed plus x plus 1, I get this guy right here. And this is very difficult to solve algebraically. However, if we let the calculator solve it for us, we're in good shape. And we do that by letting y1 equal the left-hand side of that equation, y2 equal the right-hand side of that equation, and then we appeal to second calc intersect. And when I do, I get x is equal to 1.2134 as the solution to this equation, which means that it is also f inverse of 4. Well, we now have the two pieces that we need. 1 over f prime of f inverse of 4 is equal to 1 over f prime of 1.2134, which according to our derivative is 1 over 3 times 1.2134 squared plus 1. This is a perfectly good numerical answer, and we can leave it. If your inner nerd feels compelled, and you can simplify that. And when I simplify it, I get 0.1846 as the slope of the line tangent at x equals 4. Well, I hope these three examples have helped to clarify how